The following content has been provided by RWTH, Aachen University.
All right. So welcome to this week's lecture for iOS. This week are the last two lectures that we have. So from next week on, you will give the presentations here with the seminars. So the first two groups, please stay after the lecture today, that we can have a brief discussion over your slides, have a brief overlook of what you want to say, and that we can take a look at that. So today we'll talk about ARKit, and first a little bit about AR and where it places. So if you have a continuum spread from the real world, saying completely physical, what we all see at the moment here right now, and the virtual environment, you have basically a larger spread. So real environment, everything physical, virtual environment, everything virtual. Think of your VR games or any games that you play on your computer in particular. The whole environment that you have there is completely virtual. And between those extremes, the elements can shift a little bit around. So that is what is called mixed reality, that you have a large breadth there. And augmented reality is closer to the real environment here. So augmented reality, you have digital information that are embedded in the real world, in the real surrounding that you have. So this T-Rex here, for example, that is standing on the basketball court. Then a little bit further is also augmented virtuality, and that is something that's lesser known or lesser reported, and that is where the environment is more digital, but there are real elements baked in. So think of it, if you look at this, what you see could be completely virtual. You have a VR glass, but maybe there is actually a table at this location. It just doesn't look like that. But if you go there, you could actually use that, and you could place objects on there, and you could not walk directly through it as it would in a completely virtual environment. So the important thing, or the only thing I want you to take away from here, augmented reality is not virtual reality. There is a distinction between them. And the augmented reality that you see on mobile phones is usually the one that is closer to the real world. There are only a couple of digital items there baked in. And as a rule of thumb, if the surrounding environment that you have is more real, then it is augmented reality, and in virtual reality, the surrounding is more virtual. So for augmented reality, there are usually two questions or two problems that you have. So the first is, how do you show what you want to see? So how do you show digital information in the real world? And where do you show them? So how do you know where you need to place your digital objects? For the how to show it, it's basically the different display technologies that you have. And they range from head-mounted displays, such as the HoloLens, over spatial projectors that project on the surfaces in your scene, or handheld ones. So that is where the iPhone and ARKit fall in, that you have your normal smartphone, and you can view digital information on that directly through your camera feed. The question on how to show the information is a question about the tracking. So what elements in the scene are you able to track? Or how do you figure out where should the digital information be placed? Because if you think of it, if you just have your camera and you look through that, how would the system know where to correctly place digital information that they seem to be in the real world? And there are a couple of things that need to be tracked if you want to have a believable interaction. So one is the scene surrounding what you have here. The other is the viewport. So how does the system detect, okay, if I'm moving my phone around, how everything shifts. How does the user look at that? For head-mounted displays, that is then usually the head and the eyes where they are placed. And then for input, if you want to grab objects or if you want to interact with them, how do you detect that? Again, on a smartphone or the handheld AR, it's usually now the touchscreen, because the technology to detect your hand in that needs further research, and it's not that precise at the moment. But it will come, apparently. So for the tracking, how does the iPhone, in this case, do that? So one thing that has been around for a long time is that it uses the inertia sensors and the gyroscope in the device itself to detect changes in movement. So imagine that, well, if you start the AR application, it just places a sun or solar system 1 meter in front of you. So 1 meter in front of the device, and then it just detects the movement, and by knowing, okay, it's going into this direction, so I need to shift the virtual object into that direction, or moving it around. But that is only, well, if you have objects floating in midair, you wouldn't detect surfaces with that, and could place objects that are standing on there or dependent on where you're looking. And so what then recently came to ARKit, or what is the major part of ARKit, is using the cameras. And also that has been done before, but the advantage of having a framework that is provided by the manufacturer of the phone is that he knows exactly what sort of parts are built into the camera. So it knows exactly what is the aperture, what is the lenses that are built in. So by detecting with the camera the surface and how elements in the scene change, it can detect or estimate where are surfaces, where are elements, and so what does that mean for my environment. And the iPhone uses for different features or different applications, different sides of the phone, so different cameras. With the back, it's using or it's enabling something like word tracking, meaning detecting the surfaces that you have. So by moving around here, I could look through my phone and see objects that are placed on surfaces, on the table, on the floor, hanging on the wall, or whatever. So detecting the surfaces there. And then if I move around, well, they seem to stay there. So there I can shift my position, but the object appears to be in that real physical location. The other sort of tracking is face tracking. For that, it uses the front-facing camera and the, I'm not sure what they call it, the depth camera that they have, also for the Face ID. And it allows to track the face looking at the phone. So you're seeing then what the phone is tracking there. And what this enables is, for example, filters that you have, masks, or the any emojis that are in the recent iOS. So if you want to enable something like this for your project, there are two main things you need to set up. One is called the ARConfiguration, and the other is the ARSession. The configuration essentially means what sort of things is your system now looking for. So what are the camera and the different tracking algorithms looking for? And you can have world tracking, that is the one that really looks for surfaces, and whatever you enable tries to determine the position of the phone in relation to the environment completely. There you have the orientation, which is just relying on the movement of the phone, so you don't really care about, well, surfaces that are around you. You have image tracking, that if you define a certain image and you want to see where that is, to place an object on top of that image or information related to that. Think of a picture at a museum that you hold your phone, and on the sides now it displays information about who painted it or stuff like that. That could be done purely with image recognition. You wouldn't need world tracking or any other thing for that. And then face tracking, yeah, to enable information you want to do with the face, displaying something or some information there. On the side, or that is all for the tracking, but there's also object tracking that you can enable. And for that, there is the object scanning configuration that allows you, prior to using or detecting the object, to actually scan it, so that you can take an object that you have standing around and can scan the information of that object to pass it on then to the configuration that it tracks that in the next time. This configuration then basically sets up what should be the system be looking for, and the session then actually starts and handles the information coming from the different sensors. So managing the camera, managing the motion sensors, that they are enabled, and the information brought together. And also, this is really intensive calculations for the device. So you should take care of not having it enabled if you don't need it. So, and that is, so first when you define a configuration, you pass it to the session that is then running, or that you ask it now, okay, now I want the calculation to be done, start with that now. But if the view disappears, you should also pause the session so that it's not running in the background, eating up the battery while something else is being displayed. And you see here, well, the session is attached to a scene view object here. I won't go into details about SceneKit or SpriteKit or other elements there, because we have also a talk about SceneKit. But for the rendering that you're doing, you have the choice of different rendering technologies. So you can use Metal, you can use SceneKit, you can use SpriteKit, whatever you want. And for AR, SceneKit and SpriteKit actually have dedicated views for that. So ARScene View or ARSpriteKit View that help you to just display that. And the session property is there already then enabled if you use SceneKit for rendering. So if you use the AR world tracking configuration, there are a couple of things that you can tell the session or then the device to look for. So first, or probably a straightforward one, is to look for planes. And so here, that is just coloring in the planes that it had found and can distinguish between horizontal and vertical planes. You can look for images. So, well, can't really see that here a lot. But yeah, there is a box just, or a plane above the image. I've moved it here a little bit around so that you can see that it's not just the image colored in. Like I said, you can also track different objects in the scene. And something else that the world tracking configuration also allows you to do is create a world map, essentially a description of the surrounding area that you can then use either for persistence, meaning if I now close the app, leave the room, come back later and start it up again, that the elements are staying at their position they had before. Because if it just tracks the scene, I mean, it doesn't know where that is now. If I track these tables and the floor here, could be anywhere. But now that if I come back and it detects, okay, I have a couple of the tables here, I know that I've tracked that before, can place the objects again onto that. And what you can use the world map also for is to share the scene then between different devices. That if more people are looking at the same scene, they see the same digital information on there. So getting a little bit deeper into the scene view, one advantage that it has using a dedicated ARScene View for that is that the coordinate systems of both the ARKit and of SceneKit are directly aligned, meaning that if I place an object, I don't need to transform there between different coordinate systems. If ARKit tells me, okay, there is an object that is at location 333 or whatever, then it is also in the SceneKit coordinate system at that same location. So I can directly place the images or the elements in there. And in fact, what it does is that the camera that you control by holding your phone is the same as the camera then in the SceneKit system. So you can directly use those information. And the scene view also offers a couple of helpful information that you can enable. So first is that you can enable to show basic statistics about the frame rate that it's updating, how many feature points have been detected, stuff like that. Or enable more debug options like showing the origin, that you can see how your objects are placed in relation to that. Because sometimes you place things and it's just because or the phone started in different orientation, so your camera system looks a little bit different than you expect. And showing the world origin really helps figuring that out. And also to show the feature points that the system is tracking or seeing, and it's using these feature points to determine where are surfaces, where are elements, and stuff like that. And also the scene view has a delegate protocol that handles then all the information that come in from the tracking that you can react to that. So if a plane has been detected, you get a callback via the delegate so that you can react to that and place some object onto there or just keep them in memory. So talking about feature points, if you enable them, this is something you can see, or we'll see that you have a couple of or a lot of different points there. And those are the features that ARKit detects and can track over multiple, or while you're moving through the scene. And the more points that it can see, the more points that it can track, the more stable the whole experience will be. So to detect those feature points, the environment needs to have a couple of conditions. So the texture in the surrounding area should be not too plain, that you have some features there that the camera can detect. You have a full reflective or white board, it can't really see where different points are and track them over the time. Lighting, of course, is then also important. Completely dark or too dark, hard to track. And not related to the elements, but to the movement of the camera. If the camera is moving too fast and it's getting too blurry, it's also hard for the system to keep points in view, so to track them, what is now the movement. It is alleviating that a little bit by taking also the motion sensors into account, but if it's taking too long, then those get not very precise as well, so that it has then issues. So, and if those feature points have the same, or a lot of these feature points have the same y coordinate, so the height essentially, then ARKit can detect or say that they are in the same plane and use that to define that a plane has been recognized. So to look for these different surfaces, either flat or vertical, you just attach it to the configuration, so that you just tell the configuration, okay, plane detection, and you can specify whether you want to look for both or just vertical or just horizontal one. And then you have to implement the methods for the ARScene View delegate. And there you have a couple of these render methods. And the most important one then is here, did add a node for a specific anchor. That is when the system first detects a new surface. That is the callback that you get. And then you have different ones for the update or remove. If a plane now was thrown out, that you get a information, or update. So updates can be, for example, if multiple planes have been detected and now ARKit recognizes, okay, they are bigger than I thought, or they are in fact belonging to one big scene, then or one big plane, then it will also call the did update method that you can react to that. So, and the important thing that is passed on there is this anchor here, because that is specifying what actually has been seen. And one thing you could do is, well, cast it to be a plane anchor, or check whether it is actually a plane anchor or not, or something else. And then check whether it's a vertical or horizontal surface, and then react to whatever you want, attaching new objects to that, new nodes, what you want. Quick question there. There's no default statement in this switch statement there. Why is that? Does anyone know or have an idea? Because we learned that a switch statement usually needs to have a default block, right?
Because it's an enum.
Yes. And why do you think? I mean, I could also need to have a default block in enum.
Because it can only be horizontal, vertical.
Exactly. So since the alignment is an enum that only can take two states, or if we cover both states here, it's already exhaustive, so there can't be a default or a different result than being horizontal and vertical. So that's why we can drop that. So just as a sidetrack there. So for the anchors, there are different anchors for all the different elements that you can track for. So if I'm tracking planes, the system will return plane anchors. If I'm tracking for images, I get image anchors and so on. So, and all of these anchors then have specific properties that are relevant for this sort of feature that I'm tracking. So, for example, if I'm tracking a plane, I get information about whether it's a horizontal or vertical plane, where's the center, and what is the size, the alignment. I also could track the specific geometry of the plane, so that if I have, well, this might be a little bit too little, but if I have a rounded corner, that the geometry just not tries to make a rectangular plane, but has a estimation of the roundness that you have there. But holes or, what is it, convex or concave? I'm always messing that up. Not sure. Whether there's a thing cut out, it will only have the, it won't track that. So you always have a, I think it's concave, probably wrong. Not holes, that's the important thing. Or if you track an image, you can get access to the actual reference image that is linked to that, so that you can react to the name or the specific image, because you're looking for image groups that you can react to those, or the size. And how would you set stuff like that up if I want to look for an image? It's also done in Xcode. So you have this assets folder there, and you can create an AR resource group for that. specify this and just throw in an image and specify the real physical size, physical properties of that image. Because then ARKit, when it detects that image, can estimate, okay, where is it in relation to the camera? If it knows it's an image that is 20 centimeters wide, okay, then can see where is it and how is it in relation then to my camera. They can update stuff like there. And then in code, to define what you're looking for, you first load this group by specifying the reference images and then passing them on to the configuration by setting the detection images to that group. And then you will get a callback once the camera sees that particular photo or one of these photos, all that are in that group. But now if you would move the image around, the update there is, well, quite slow. So if you decide to move the image, it will lag a little bit behind the update of that change. And to help with that, you can also set the maximum number of tracked images. Tracked images meaning there it's a more fluent update. So once it sees the image and you move it around, it will be much more stable and try to match the real location of the image. And then in the callback, or whatever callback you get, where you get then an AR image anchor, you can access the reference image property to get information like, well, the name. So if you're tracking more images, you can see which one is now the one that was actually detected, and also the physical size. So you can react to that and have maybe something that is overlaying the image there. For the images, there are a couple of guidelines or rules that you should follow. So first is that the images should not have transparent data. So it needs to be full white if you want. Is it full white? Not sure what it will then leave out, but it should be, so not have transparent data and a high contrast as well, so that it can easily detect the different properties, elements of that image. And it's a trade-off that you have to make. A higher quality image will be easier to track and to detect, but it also increases your file size. So if you're tracking 50 objects or 50 images, I'm not sure if there's a cap for that actually, and all of them are higher resolution images that are very large, then it increases your file size of your app and run into issues there maybe. Yes, so what we've all looked at, or what we've looked at so far, is how do I react to the environment and how do I know where and how to display my digital content. But the other side that you need to look at is how do I interact with that? So how can I interact with the space around me, with the physical environment? So, and how that works, like I said, so far you're using the touchscreen for this. So, and what happens when I touch the screen is then that you cast a ray into the scene and just look, okay, do I hit something that the system has already tracked, that the system already knows? And the way you do that is 2 steps. First, if the screen has been tapped, you need to get the precise location that is then in the scene view. So if I'm tracking or detecting touches over the whole screen, but only a small portion is the scene view, that I can tap on that the scene view knows exactly where has this tap occurred, because that location is then used to perform a hit test, that you ask the scene view, okay, from this location, cast array into the scene and look for elements that you find. And the different elements are here defined by the types array that you pass. And those types can be a lot of different things. You can look for individual feature points. You can look for the different planes that you can just where the system thinks there might be a plane, or where it has actually already tracked a plane. And the plane can then also be simplified by, well, either just the original plane that was detected, or using the extent that was tracked, or the geometry. The more precise or the more concrete you get, the more cost intensive it is also. So then what you get back is an array of hit test results. And the hit test results are the elements that were intersecting with the array that you cast. And for those results, you get both the type and the anchor if one was hit, and also information like the distance from the camera and also the transforms. Transforms meaning what is the transformation from the camera to the point that was hit, so that you can apply this to your digital objects so that they are inside or sitting on top of the anchor, the plane, or whatever was hit. And which is, transforms can either be world transforms, meaning how is it in the global scale, or local transforms, how is the transformation from the closest feature point, from the closest element that was tracked to that location. So that is a brief overview over ARKit. Any questions so far before we start with the demo? Just in general for this. Then I would say we continue with the demo. If there are problems, then maybe they clear up over that. So for ARKit, there's also a template that you can use, augmented reality app here. Let's call it like this. And like I said, for the content technology, so what is used for the rendering, there is you have the choice here between SceneKit, SpriteKit, and Metal. So we will stick with SceneKit. Let's place it there. All right. So what is then directly set up? You see here you have this art scene code, SceneKit assets, and there's this ship that is set in here. You can load your own objects into there. Here we have the mesh of this the ship. Then in the main storyboard, let me just also, before I forget, increase the size. We can see that. So in the storyboard, you have in your view controller also a scene view. And the scene view is what is used to display your AR scene. And also what is automatically been added in your plist, that you have the flag for the camera usage. Because when your app wants to use the camera, needs to ask for the permission. And this flag you can specify what needs to be tracked or what needs to why you need those access, that you can inform the user of this. For the device capabilities, that you can specify, okay, this needs to use ARKit, that apps that if you browse the App Store with a phone that doesn't enable ARKit, I think from 6 it was enabled, not sure if 5S was in there, but they won't even see the apps then if they're not capable of running that. So in the view controller, there is that large enough, or does it need to be larger? Probably a little bit, right? There. Let's try that. So in the view controller, we already have connected our ARScene view, and in the view.load, set ourselves as the delegate, so that we're telling, okay, we're implementing the ARScene View delegate, specifying that the statistics should be shown, and then load the ship scene that is defined in the here in the assets, and specify that scene to be our scene that we show. In the view will appear, we are specifying the configuration. In this case, yeah, using the world tracking configuration, so tracking using every sensor that the phone can use to track its position, and then also run that configuration. When this view disappears, that session is then paused, yeah, to save the performance there. So if we want to see a couple of more information, we can just add here to the debug options, and we want to track show world origin, that we see where is the origin of our scene, and also the feature points. So let's check that out, but first, when I tested it out, it was, let me unlock it here. Hello. So while I was testing it out, it was running not very smoothly on this side. So if that is lagging on the phone, it's actually a little bit more performant. So let's just move around. But let's hope it's good enough so that that you can see what it is about. So the first time, it should now ask me for permission to use the camera. So yes. And then it's tracking here now the environment, and it's running more smoothly than I expected. And you will see, or you can see the feature points that are tracked there. Those are these small dots that are then shown. Those are the points that ARKit uses to track its location. I can show here more information. So about right now there is nothing in there, so the frame rate is quite high, but I could also see how much is taken by the animations, by calculation of the physics, and so on, so that I can react to that if that is too much. So let's stop there. So let's try to detect planes. So what I need then first is to tell the configuration to look for planes. And the way you do that is just tell it, okay, plane detection, it should look, let's say, looking for both. So horizontal and vertical. That I'm checking for both of these planes. And then I need to implement the delegate method that I get notified when such a plane has been detected. So we have here the did add node for an anchor method, And in there, so here I will just check whether it's a plane anchor that was passed. Am I trying to cast it to be a plane anchor? And if not, I don't care at this point. So now I know that the plane anchor is actually a plane anchor. And just for now, I will want to create a horizontal plane at that location. This is a method we will now implement that will return a node. And so at the moment, it doesn't know what create floor is, but we'll implement it here. So this method uses SceneKit, but since we will learn about SceneKit a little bit later, I won't go into too much detail there. But we have just create floor, and it returns an SCN node. And to create that node, just create a bare one first. Create the geometry, which is what is the geometry that should be shown at that location. Here we just want a plane, and the plane should be 1 meter by 1 meter. So the measurement unit in SceneKit and ARKit is in meters, or in ARKit more to say. Then the geometry of our node, set that to this geometry that we just created. The nodes or the planes in SceneKit are usually not flat then if you add them there, so you need to rotate it by 90 degrees. Let's do that by adjusting the angles there. And like I said, this is now not the most important part for understanding ARKit, but just that we have it here and return that node. So what this did is creating a flat plane at the location since we added it to the node that was here detected. So let's see whether that worked. So now when it detects a node, it should color that in. So you see there, one. If I move around here, we'll detect more here. There's not really a plane. But what you can already see is that are multiple planes or not extending if it detects that there are, in fact, more stuff. And that is since we just react to the initial plane that was detected and not reacting to the updates. So next, let's do that. So let me look at that. So first, what we want is then essentially that the plane that or the floor that we are creating should be matched to the size of the plane that is currently detected, or by the plane anchor that is passed over. So let's change this to take an AR plane anchor and change it so that the geometry here, the size of our plane, is dependent on the size of the anchor that was passed over. So look for the plane anchor, the extent that we have, so the size of this, and here the height. And like I said, the coordinate system of ARKit is the right-handed one. So the Z dimension is pointing towards you. If you just hold your hands up, X, Y, and Z. So X and Y are the usual Cartesian axes, and Z is pointing towards you, meaning a plane. If we have there the vertical one, horizontal is then easier to decide. The X and Z dimension are specifying the size of the plane. So that is why we use X and Z here. So now that uses the information from the plane anchor. And let's just pass this over here. And also then implement the update method. Here we have did update node for the anchor. And again, here we're just checking that we have a plane anchor. But also we want to see the node that is attached to that anchor. Since we got the did update for this specific node, and we know if we had a plane anchor before, we added a node to that, a plane node to that. So like we saw with SpriteKit, SceneKit also uses the scene graph. So you have different child nodes that you attach to a node. And so the first element, if there's something in there, that would be the plane. And then the actual plane that we have, the geometry, we want to have that as a plane. Since that is what we added there. Yeah, so just to go over that a little bit slower, we first check that the anchor that that was passed over is a plane anchor, because we want to react to that. Since we added for when we first saw that anchor a node, our floor, our plane to that anchor, we check that the first element in there that we get that node, and that node should, the geometry of that node should be our plane. So we unwrap the geometry of that particular node as a plane, so we get that. And then we just update the position of this node so that it is now in the newly found center when the plane anchor updated. So the vector, plane anchor, center X. 0 for our Y, since it's not relevant here, or it is attached to the anchor. And then the plane node, not plane node, plane anchor, center, and Z. So that centers our geometry of the plane in the center of the plane that was detected. And now to change the size, we adjust the width. And the casting is always necessary, since here, as you can see, the extent is a SIMD float 3 and not the CG float that the width property takes. So there's then some casting involved. Set the width to the X extent and the height to the Z extent. All right, so that should then help that the planes are updating with the newly found information that SceneKit gets, or ARKit gets. So here we have the floor, and you can see if I move around, this floor is now then updating. It says, oh, here's also the plane. I think we didn't see that before. So that is then attached there. And if I go up here, this is now then a new plane. So since this is now then size here of our disk, and it updates the more information it gets. Any questions so far? All right, then let's continue with image tracking. So for image tracking, let's use this example. So we have this photo of androids, and since I'm working at this chair, this should not happen. So every time the camera is seeing this image, it should just block it so that no android is seen at this chair. So for this, I add a new resource group. And I can specify then here the elements that should be looked out for. So here I have my image of androids. That one. Let me just pick it up. Come on. There we go. And you can see there is a warning that, okay, it doesn't know what is now the actual physical size of that image. So I have to set this, not in meters, but in centimeters. And it's 20 centimeters wide. I will automatically then detect or calculate the other one. So by having set that, I need to tell our configuration to look out for that image. And for this, first I need to detect get the reference images by querying the particular group. Reference image in group named. What we had was AR resources, and you can set that however you want. Bundle, I don't care. And we also force unwrap that because we hope that it is there. Of course, you need to take more care of that because it will crash if that group does not exist or it can't find that. So, and then we tell our configuration to look for these reference images. So far, we only have one in there. But yeah. Okay, now our did@node method is notified for different anchors. So instead of this, we will just switch over the anchor and then decide based on what anchor was passed over to what we do. So first, for the existing functionality that we have here, if the anchor is a plain anchor, then we will just do what we did here. That we create our floor and be done with that. But if we have an image anchor, then what we want to do also create a first get the image that was detected by asking our image anchor for the reference image. And then let's create a plane that is then passed it over that image. So we create a plane that has the width of the reference image. So there you access the physical size property of the image that was passed. And for that, we will take the height and give it a red color. Again, that is something UI color red. And create a node with that information. and rotate that node. Again, so that it fits our size. And then just passed it over that location, that node that was passed to us. So add child node, the plane node. And the default block is just, no, not private, print. Should not happen, but just that if that should be the case, that it's shown there. Then let's go back to our app. So still feature points and the plane is detected, but when I come over there, that image is not shown. But as you can see, if I move it around, the visualization lags a little bit behind. And that is why if you want to continuously track those information, you also need to tell the configuration that it should do that. So here we just add the maximum number of images that are tracked and set it here just to 1. Because we only have one image that we want continuously tracked. Again, move that here. So and now, once it has been tracked, if I now move it around, it's way more stable and not showing that image that is underneath there. If I bend it too much, then of course it will not work anymore. All right. So far for that. Last thing that we'll add here is that we react to tabs on our screen. And for that, we'll add a tab gesture recognizer to our scene. And just link it up to, where is put it there. So here from our tab gesture recognizer, create an action that the screen has been tapped. And creating that IV action there. Where was it? Edit here. And so what are the two steps that we needed to do was first finding out where the touch happened, and that is that we get from the sender where is that location in the view that we are interested in. So here in our scene view, and with that location we can perform the hit test by casting a ray into that into the scene. So perform a hit test from that touch location that we found, or that was passed to us, and here existing planes using the extent that we want from the planes that we were tracking. We want to see where we were where we hit those. To check, so the first result, or the first element in that array that is passed over or returned is the first element that was hit. So we just take the first element and see whether there was something in there. If so, then that is the first element. And what we want to do, we want to just display the ship that was now flying around here, just add it to that location. So we get the ship by getting that location. Let's see. and want to get the root node of that. And with that, we need to place it at the location that we found. And as I said, that from the hit test, we get the word transform that can specifies the transformation that we need to apply to this element. So again, I need to cast that information. So we have the result and the word transform, because one is again a different format. And then apply that transform to this ship that we just created. And also, so that it doesn't block everything, we set the scale to 20%. All right. And add it then back to our scene view that scene action. So now let's see whether that worked. So now, when we're tracking our scene here, I just tap somewhere, and we have our ship added to that location. So now we have one here, and can react to those touch events. And one over there. All right. So now we have an armada, no, not an armada, but a couple of them flying around here. So that concludes also the demo. Any questions about what was now shown here or the information before? Anything that is unclear or completely disturbing to look at, to hear, or whatever? If that is not so, oh, what is it flying around here? So probably the recording is then not very good. Yeah, so that then concludes the lecture for today. Please, the groups, I think we have map kits and class kits today. Please stay here. We'll spend then a bit on looking over that. For the others, this is the end for today. And yeah, see you again tomorrow.
This content was provided by RWTH, Aachen University.